Today we will discuss about electrostatics of conductors. Here we already know that in electrical conductors free electrons exist. Free means the outermost electrons of atoms have freedom to move randomly in different directions, but they don't have a net direction along which they can move. So, due to these free electrons, when an electric field is applied, they become mobile and electrical conduction becomes possible. Now, here we discuss about solid conductors. There are conductors in liquids also. So, in electrolytic conductors, the charge carriers are both positive ions and the negative ions. But here we will discuss only about the electrical conduction in conductors which takes place due to the free electrons present in the conductors. So some of the important characteristics of such conductors are listed here. Now, first point is inside a conductor electrostatic field is zero. So this was already explained in the previous classes. That is, in static condition means the charges are not mobile. So there is no net electric field acting on the charge carriers. Therefore, we can say that under static condition, when the charges are not mobile, it means the net electric field must be zero. So in a conductor under static condition, the field at every point is zero. Then second one is at the surface of the electrostatic conductor, at every point the electric field should be normal to the surface at that point. So already this is also explained. If the field is normal, then what happens? The component of the field will act on the surface or tangential to the surface, and a force acts on the electrons, and hence they become mobile. Then electrical conduction takes place. But we are talking about static condition. So the electrostatic field should be always normal to the charged conductor on the surface. Then only there cannot be any flow or mobility of the charge carriers, and there will be no electrical current. So because we are talking about static condition, the electric field at the surface at every point should be normal to the surface at that point. Then if you give any excess charge to the conductor, that charge must reside only on the surface. It cannot reside inside. So this is from the first point. So you have given charge means. So let us consider a small volume element inside the inside that conductor. So since the electric field is zero at every point, as I said in the first case, therefore if electric field is zero, and from our Gauss law, flux is given by Q by epsilon, and flux is also equal to E bar dot ds bar. So if I say electric field is zero, then automatically this relation tells us that Q must be zero. Otherwise, the electric field cannot be zero. So therefore, since the electric field inside the conductor is zero, any charge given to the conductor must go to the surface only. It cannot reside inside. That can be proved from this simple relation. Another thing is the electrostatic potential at every point inside the surface, inside the conductor and on the surface must have the same value. Because as I said in the earlier case, at the point the electric field is zero at every point inside means, therefore the potential of such a conductor under static condition above on the surface and inside the conductor must be same. So no work is needed to move a charge inside the conductor. But the potential will be different at points on the surface of the conductor and a point outside the conductor. Then we will come to the next point, that is electric field at the surface of a charged conductor is given by sigma by epsilon naught. So this can be derived like this. Consider a charged surface. So let us suppose the charged surface is there. Now select a point P and imagine a small elemental area and something construct a Gaussian surface over this, something like a pillbox. So this is a pillbox. So let us suppose this is a charged surface and let us consider a point P where you imagine a elemental area ds and let sigma be the charge density. Therefore, the charge enclosed within the surface is sigma ds. Therefore, from our formula, that is from our Gauss law, so the electric flux, electric flux is given by total charge enclosed in the Gaussian surface by epsilon naught. But Q is nothing but sigma ds by epsilon naught. But in terms of electric field, E is given by E into, that is phi, flux is given by E bar into E bar dot ds bar. Since the area vector and electric field vector are in the same direction, we can put it directly like E ds. So equating these two. So E ds is equal to sigma ds by epsilon. So the ds cancels. Now, if you imagine a unit vector radially outwards, if the charge is positive or if sigma is greater than 0, you say the surface is, the conductor is having positive charge. In such case, in vector notation, you can write sigma by epsilon naught n cap. So the field will be radially outwards or in the outward along the outward drawn normal. If the sigma value is less than 0, then the electric field direction will be radially inward or towards the inward drawn normal at that point. So therefore, the electric field at the surface of a charged conductor is given by sigma by epsilon naught, and the direction of the field is along the outward drawn normal if sigma is greater than 0. That means if the conductor has positive charge, and inverse if the charge is negative. Then what is electrostatic shielding? And it is already explained while discussing about the electric field inside a charged spherical shell, in a uniformly charged shell. Inside that, at every point, field is 0. So that was already explained when we discussed Gauss law also. So the electric field, this electrostatic shielding, if you have a cavity inside a charged conductor, so you have, suppose this is a conductor, so you have a hole inside the charged conductor. We know that the charge resides on the surface and the field at every point inside the conductor is 0 from this first point. Therefore, the field is 0 inside the hole at every point. So, that is inside the cavity, the field must be 0. Therefore, this concept, we call it as electrostatic shielding. So that means since electric field inside the cavity of a conductor is 0, any sensitive device kept inside such a cavity of a conductor is protected from outside electric fields. So therefore, we call it as electrostatic shielding. Okay, so these are the important points regarding the electrostatics of conductors.